and we're here to talk about antibiotic resistance. So how many people here have used antibiotics? So what if I told you that according to the CDC, 2 million illnesses and 23,000 deaths have been associated with antibiotic resistance per year? We're going to first look at our most powerful antibiotic, carbapenems. These are considered our last resort antibiotics since they're used for treatment of infections caused by multi-drug resistant bacteria. However, CREs emerged. This resistant bacteria can cause bladder, lung, and blood infections that can lead to death. And in 2003, the first CRE strain was discovered in Brooklyn Medical Center, and within a few years, it spread to hospitals worldwide. But before we go any further, let's break down how antibiotics work. So antibiotics have multiple methods of inducing bacterial cell death. Rifamycins inhibit RNA synthesis by binding to the subunit that synthesized RNA comes out of, and thus causing cell death. Others, like carbapenems, inhibit cell wall synthesis and kill the bacteria that way. Another major way that antibiotics work, however, is by blocking DNA replication via quinolones. Quinolone antimicrobials are able to interfere with DNA replication by targeting topoisomerases, which we learned are enzymes that are in charge of cleaving and rejoining DNA strands during replication. By trapping topoisomerases 4 and 2 at the replication site, quinolones are able to cause DNA breaks and trigger cell death. So what does this mean, though? In the U.S., we needed a prescription to get antibiotics. But they're still really much overused. In 2010, the CDC found that for every 1,000 patients, 850 to 900 antibiotics were being prescribed in Massachusetts alone. So if a person can't get a prescription, they can also be really, really shady and buy them illegally in a bodega or online. But what does this mean for resistance? When we use antibiotics, it actually just eliminates all the good and bad bacteria. So only the resistant ones remain. These resistant bacteria can then spread and repropagate and spread their resistance via horizontal gene transfer. And these resistant genes then enable the bacteria to produce proteins that are helpful to their survival, such as things that inhibit the cell wall breakdown of them and the efflux pumps that are used to pump out the antibiotics. So if you think about it, people that go into hospitals for sickness already have a really compromised immune system, and with unclean conditions, hospitals are hotbeds for spreading antibiotic-resistant bacteria. Some of the strongest resistant bacteria are found here, and the spread can happen via patient-patient interaction from the healthcare providers themselves or unclean surfaces in the inpatient areas. Resistance is not a new thing. And actually, when Fleming won the Nobel Prize for penicillin, he actually warned against this. Scientists thought that with prudent use of the powerful antibiotics, such as carbapenems, we could hold off the evolution of this resistant bacteria. But it is becoming clear that resistance is spreading quickly. And some of these ways are these are some of the antibiotics. In hospitals especially, many people are at high risk of contracting it. So when this is present, chemo patients and people with arthritis have really compromised immune systems, and they're really at risk. People that are getting surgery are at risk of contracting it via their surgical site. And after these people leave, they can spread it to their community, and a shady way is also through food too. But with antibiotics used in hospitals and like the resistance spreading, it's hard to believe that a lot of countries actually lack information that tracks these resistant bacteria. And also, only 5 new classes of antibiotics have hit the market in the last 45 years, and we're running out of options since Big Pharma is not investing in forming these new drugs. However, we're thinking of new ways, such as tweaking current drugs. Scientists begun altering the chemical structure of current antibiotics to get new uses for them. So, for example, ADEPs are antibiotics that never made it to the market, but some scientists have begun strengthening their hydrogen bonds in order to make them more cell permeable. By using this, we actually were able to successfully treat staph infections in mice, and we're also looking into combining modern antibiotics. So going back into ADEPs, ADEP4 was basically seen as a failed antibiotic. However, when a microbiologist in Northeastern combined it with rifampicin, the combination actually completely eradicated MRSA in mice. So ADEP4 uses a special protease to break down the proteins, and this combination allowed the bacteria resistant to ADEP4 to be killed with the combination of the use of the rifampicin. Adjuvants can also be used combined with antibiotics in order to resensitize them to the resistant bacteria and increase their susceptibility to antibiotic treatment. So they work, adjuvants work by like protecting the enzyme degradation of antibiotics or inhibiting those bacterial humps, so they then can be re-killed, I guess. But the best way to fight antibiotic resistance lies within the healthcare facilities. So now greater emphasis has been put on hospital tracking so that physicians and pharmacists are being held more accountable. The practice of antibiotic timeouts also encourage reassessments of antibiotic strategies 48 hours after initial treatment of the patient. And to bring this all back to CREs, actually in 2008, a new strain of CREs, scary, was discovered and to be using a completely different enzyme that breaks down carbapenems. This new strain is evolving faster than we're able to control, and the CDC reports that there's at least one strain of CREs in healthcare facilities across 44 states. So this brings the question, are we entering an age where due to the rapid spread of resistance, a simple cut can kill us? This brings us to our propositions.